moved as a postdoc to the physics department of UCLA, okay, before joining Purdue, and he sort of works on magnetism applied to broadly spintronics, and he also has recent interest in quantum computing type of stuff. And he's a very young faculty, but his publication record is very, very impressive. He has a large body of publication already. And he also got NSF Career Award, and it seems like he is an excellent teacher also. He got a couple of outstanding teacher award already. So please.
Thanks, Mukul, for that kind introduction. I'm very happy to be here. Should I use the mic? Yes.
I think it will be better here. No, that's this.
Hello, can you hear me?
No, it doesn't.
Probably muted. There's a mute button at the top.
That's okay. If it's, I can just speak loudly.
Yeah, that you can do. But yeah, that you can do. Yes. Oh, microphone coming. Take it.
Am I audible better now? Thank you. Yeah, so thanks for the kind introduction and this opportunity to present our work here. Today I'll be talking about, mostly as Mukul mentioned, I work mostly in the field of spintronics and magnetism related work. So here today I'll be presenting a sort of a direction which within the spintronics community is gaining a lot of attention, which goes by the name hybrid quantum spintronics. Before I do that, let me just start by acknowledging the people who really did this work here. So most of the theory work that I'll be presenting here, so I'm kind of an interface between theory and experiments. So most of the theory work is done by Avinash, our postdoc here, who's now shifted from our group to Intel now. And the grad student was Mushfiqur Rahman, who did the theory work. We also had a nice, bright undergrad intern from IIT Bombay visiting us, and he contributed to some of the work today as well. Most of the experiments that I'll be presenting were done by Abhishek Solanki, who is the grad student. And of course, a lot of this would not have been possible without the collaborators who are listed here. Specifically, the initial works that I'll be presenting was done in collaboration with Amir's group. So I'll keep on highlighting whenever work I'm going to present with whom we collaborated. And I should also highlight here, since there's a IHub, there's also a similar sort of quantum science center at Purdue right now, which is led by Oak Ridge National Lab. So they are supporting a lot of work here, so I should acknowledge them. With that, let me try to give you the overall sort of view of spintronics in one single shot over here, one view of such field, where essentially the idea is you are still kind of like user inspired at a very global level, trying to come up with new sort of memory, computing, sensing, and communication technologies. And for that, the field of spintronics tries to do that with exploiting the spin degrees of freedom of the system. And in order to make this connection, sort of a large number of in order to make this connection, there have been sort of a renaissance of fundamental physics and phenomena that people have discovered, and primarily that has occurred along two separate paths. One of them is in the so-called macroscopic limit, where you can think of the spin. In this case, just behaves like a classical vector. In general, it is a quantum object, but in the macroscopic limit, it behaves just like a classical vector. Here, people have discovered various kind of building blocks in these classical systems. One of them being nanoscale magnets, another being you can create these kind of nice-looking topological spin textures, which are supposed to be very stable objects, and as well as sort of spin wave-like excitations of these materials. People are exploiting all these different kind of building blocks, and on top of that, you can control these various building blocks via thermal, mechanical, electrical, and optical coupling to the system. So it's like a very nice universal system which couples to a lot of degrees of freedom via spin-orbit interactions, for example. And you can exploit all these phenomena then finally with the goal of constructing new type of memory communication sensing technology, where the essential idea is, as compared to charge-based technologies, if you utilize the physics, rather than abstracting the physics to zeros and ones, if you utilize the intrinsic dynamics of these compact objects, you can represent a much higher function, a greater function in all these different applications. And that's the basic idea of utilizing the spin systems for various these applications. On the other hand, parallelly there has been a lot of development on the microscopic limit, where spins really, you have to take the quantum nature of spins into account. And in that case, for example, I'm showing some of the advances that people have looked at is, for example, trapping these spins inside defect centers in insulating holes, where they show quantum properties sometimes even up to room temperature in some of these defects. And then the idea is you want to exploit this quantum coherence and entanglement for adding the quantum coherence and entanglement, which is missing on the left hand side of the picture, but you could utilize that on the right hand side to create again new type of memory computing sensing technologies. So those two parallel paths people have been taking with different goals. What this particular talk will focus on is there is a lot of merit, and this is the main message I want to give today, is there is a lot of merit in sort of combining the advances that has happened in both of these fields for advancing each of these respective fields in themselves. Because that's the main message that I want to give, and that is what I'm calling here as hybrid quantum spintronics. And this I will show by taking a specific example. So I'll pick up these sort of spin wave-like excitation from the classical macroscopic world and the spin defects from the microscopic world, and talk about hybrid structures which combine them together in some experimentally. Again, these systems this is just a cartoon representation, but experimentally you can combine spin defects and integrate them with these magnetic materials. And the reason why would one want to do that, on one hand, the main thing comes out is these spin probes, these spin qubits, or the microscopic spins. They now have emerged as very nice novel qubit-like probes of these sort of macroscopic systems, not quantum systems, but macroscopic systems. And as a result, this provides a new type of probes which are not possible before in the spintronics community, which were missing, and it has sort of filled that gap. And this is the main message that I will try to deliver in today's talk by taking these three examples. On the reciprocal end, again, I most likely will not have time to discuss the opposite side of things. On the other end, the fact that you can control this spin, the macroscopic system that I showed with charge, heat, voltage, current, you can utilize that fact to control the spin qubits themselves. So it turns out that it is very challenging for the traditional ways of just passing a microwave or strip line to control the spin defects and localize it to nanoscale, create scalable structures. It's sort of a challenging thing to do. But the advancement of utilizing these magnetic excitations of magnetic materials could provide a solution to this particular challenge. And in this respect, we did sort of two of these works where we showed, in one case, you can build sort of non-reciprocity in these circuits because magnetism naturally breaks time reversal symmetry. So as a result, if you utilize magnons for building quantum circuits as an on-chip quantum circuits, you can create non-reciprocal circuits. And on the second work over here, we showed that in fact you can locally, coherently drive these spin defects via voltage, which voltage drives the magnet, and then this magnet drives the NV center. That provides a way to drive locally these NV centers, which is one of the challenges the NV center community faces. So that is more like a theoretical proposal. So I will most likely not be able to get time to go into these two, but just want to flash them to say that if you are interested in talking about that, I'll be happy to do that later on. Okay, but for the rest of the talk, I'll focus on this first message, that we really now have 9 new kind of probes for condensed matter in general, and what I'll be using that to show for these specific examples of spintronics in the remaining part of the talk. So I'll start with this first work, and this is the work which was led by Amir's group when I was a postdoc. So let me try to explain that as an introduction. So the first thing that the goal, what is the problem statement here we are trying to do? The problem statement is, now if I have these sort of spin wave-like excitations, there is a field of magnon spintronics which tries to exploit these excitations for coherently transforming information from one end to another. These are wave-like excitations, so you can think about architectures which utilizes waves for computing, or different kind of optics kind of architectures you can map onto these microwave excitations. So there is a lot of interest in this field to utilize them for transforming information and doing computation with them. The nice advantage they provide is, because it does not require charge transport, they are free from Joule heating type of effects, and hence it could potentially be low power from these things. So that's the overall goal, to exploit these excitations. Then, in order to do that, we need to develop tools to actually generate non-equilibrium population of these. So apply some gradient of temperature, voltage, or microwave drive to drive currents. So you need to create equivalent of applying a let's say an electric field, two voltage contacts and a bias to them. And at the same time, you also need something that can measure what non-equilibrium situation you have created. So you would like to measure the voltage that these things generate. Now that turns out a bit challenging for these sort of charge neutral excitations, because typical probes of electronic charge could not be directly used. There's a lot of work that people do for using spin orbit interactions and utilize like platinum-like contacts for doing similar things, for injecting spin currents and detecting them in these systems. But what I would like to show today is NV centers is an alternate probe which can actually on a nanometer scale resolve these sort of non-equilibrium situations that we create for magnons. So that was the main problem statement we wanted to solve. So can we actually probe locally some non-equilibrium properties of these magnons? And here I'm saying that as this non-equilibrium property that we want to probe is a quote-unquote an effective chemical potential of magnons. So I should really qualify that statement by saying that chemical potential for magnons is a boson, so it should be just zero in equilibrium. And then when we are actually driving it, what I mean is when we are driving, for example, by a microwave drive to create some non-equilibrium population of these magnons, in many situations, especially in these type of material system, they quickly the interaction between them thermalize it to some quasi-equilibrium situation, which can be modeled as a Bose profile with some change of the chemical potential. So that's exactly what I mean. It's a non-equilibrium population-driven system, and that can be modeled with some change in electrochemical potential, and that electrochemical potential is what we would like to measure in situations, because with the goal of actually, this is sort of like an equivalent of a battery. If you want to measure electrochemical potential locally, can I do that for magnons? Okay, so that was the main problem statement that was attacked in this work. And as I said, it will be, NV centers will be used for that. So let me just briefly digress a bit to show that what NV center is. So NV center is a nitrogen vacancy in diamond. So you have a carbon lattice, you replace one carbon atom with nitrogen, and you have a vacancy nearby. In this defect, you can trap electrons. Specifically, the ones that we are focused here on is the so-called NV minus, where we are, the NV minus is the ones which are optically active, and you can utilize them for optically reading and initializing them. So these are the type of defect centers which can effectively be thought as a spin 1 defect, which just traps an effective spin 1 at its site. Okay. The Hamiltonian that governs this system is shown here in the absence of magnetic field, so and the level diagram is shown over there, where what I really mean is that this being a spin 1 system, the ground state, it has a triplet and singlet manifold. It turns out that the triplet manifold is the ground state of the system, and the singlets lie in the higher energy. So these are the spin degrees of freedom, but now these are charges. They also have orbital degrees of freedom. So you have excited states as well, because corresponding from the orbital degrees of freedom, and all those states I'm just drawing as this blob over here. The thing is that these are optically active. That is, if you shine green light on them, each of these levels you can take them up to the orbital state, and they come back and fluoresce. Okay, so and the nice thing that happens here is if the state is in +1 or -1, the green light can take it up, it can come down, or it can also have a dark path, so-called dark path, where you go via this singlet to the state 0. On the other hand, if the spin was initialized into state 0, it will just go up and come down. So it will keep cycling up, down, up, down. On the other hand, from here, you can transfer population to the 0. What that has an effect is, if I keep on shining green light on this, I can transfer my population from +-1 to the 0 state. So that is like initializing your qubit into the state 0. On the other hand, the same phenomena allows me to read the state, because since here it's always optical transition, this state fluoresces more as compared to this state over here. So by just monitoring the amount of light coming out of this, you can tell whether the qubit is in state 0 or either of this +-1, and on the same time you can use light to initialize the state, the system into the state 0. Now on top of this being spin, you can introduce magnetic field. So now this spin interacts with magnetic field by the usual Zeeman coupling. So this magnetic field you can think of two situations. One, when it is an AC drive which is orthogonal to this NV axis, the spin axis, then it can cause transition, Rabi, the usual Rabi oscillations between the two. So you can change this initialized state, the state that you initialize to state 0, you can change it to ±1 and bring back and forth via microwave. And if you apply DC field, that DC field splits the energy difference between +1 and -1 state. So you can change the tune, the levels, you can move these levels. Okay, so if these fields come from some environment, they change the quantum state of my system, which changes the fluorescence out, and as a result, you can utilize this to detect magnetic fields using well-established protocols in the NMR community. And again, if you are interested in looking at this general field, this is a good review article which compares various kind of quantum objects. So here the idea is you are utilizing how the quantum states evolve in the environment so that's one of the Achilles heel of quantum system, that you want to protect it from the environment. But here you turn the problem around, saying that if this is so sensitive to the environment, I can use that to sense the environment itself. And that whole field, the so-called quantum sensing field, is nicely reviewed here. So one thing I want to highlight there, so now based on years of expertise from the NMR community, you can develop various kind of protocols which allows you to sense these fields right from DC value to up to the qubit splitting. That is the energy level splitting that is shown over here. And that turns out that's governed by this parameter 0 field splitting in this NV center. For that, it is about on the order of gigahertz. So you can go from 0 to gigahertz of frequency of magnetic field you can sense via various type of protocols that is listed here. I will focus on one of these protocols that we utilize in this work, but that is the idea that you are utilizing optically using these atomic sensors to read or to sense magnetic fields all the way from 0 to gigahertz type of frequencies. Right? By the way, I'm also happy in case you want to interrupt me in the between, so just wanted to let you know. All right. So with that background, this technique is now gaining a lot of momentum in the condensed matter community, because now the idea would be you will take this defect center and place on top of some target material and utilize these target materials. If you want to probe some sort of excitation or ground states of this, you will be probing them via non-invasively probing the magnetic field signatures that they emanate. Right? So these whatever excitations you want to measure could be a magnetic noise, or you want to measure some texture, spin texture, they generate some magnetic fields, and then you use this as a magnetometer of detecting whatever protocol you want to use to detect basically from DC up to gigahertz frequency resolution of all these excitations in this system. On the other hand, by varying this distance d, how close you bring this to your target material, you can change the wavelength of the excitations that you're trying to measure. So you can vary this distance d and get a resolution in the wavelength of the excitation so the length scale that you can measure, the length scales that you can resolve in this material is governed by this distance d, which can be brought on the scale of tenths of nanometer. So as a result, you get a nanometer scale resolution, and this NV center maintains these quantum properties, this fluorescence, all the way from cryogenic to room temperature. So as a result, this technique can be applied across a wide range of temperature. And in principle, this is non-invasive in the sense that this spin is a very tiny perturbation on the target material that you want to measure. So the things that you're trying to measure will not be perturbed by the spin. Although I should sort of put a caveat there that whenever you want to measure very low temperature stuff, you still need laser to read and write it. So as a result, that laser could heat up your material and change some of the properties. So going it in very low temperature, it's a challenge, but certainly something that people are trying to push that temperature scale further down. Okay, so utilizing this, I just want to flash few examples which people have used this technique for. Again, a very good review article if you want to focus here on how this has been used in condensed matter context. You can take a look here. But some of the examples here are, for example, imaging vortices in superconductors. Because of the Meissner current that they generate, that Meissner current gives rise to magnetic field, which you can use as a magnetometer to image vortices in different materials. Here in this work, how current flows in 2D graphene, that was what was imaged in this particular work. For example, and likewise the third example of magnetic materials, this was used to image, let's say, like a domain wall texture, because whenever you hit a domain wall, there's some stray magnetic fields that are emanating right at the edge, and you can image that using this NV center via magnetometer. So you can image spin textures in magnetic materials. Okay. So now with that introduction, let me come back to the problem statement we were at. So what the problem statement was that if I create some non-equilibrium population of magnons, now can I utilize the magnetic field emanating from these magnons to tell what is their non-equilibrium population, what is their non-equilibrium chemical potential. Okay. And for that purpose, I just want to very briefly introduce this relaxometry protocol, which is utilized here. The relaxometry protocol uses the following fact that if you have this NV center and you can initialize this NV center in one of its non-equilibrium state and see let it evolve, come back to thermal equilibrium. How fast it equilibrates, that just depends on the environment fluctuations which are bringing you back to the equilibrium. So as a result, if the sample is emanating some magnetic noise, in particular transverse magnetic noise, that will cause transitions between the two levels. So if I initialize my state, let's say in the state 0, and let it relax, it will eventually go to some thermal equilibrium population, and how fast it goes, it depends on the spectral density of the noise that is resonant with the NV center. So this is the usual Fermi golden rule that we know that if utilizing Fermi golden rule, we can calculate these type of spectral densities of the noise that is emanating from sample, which is proportional to spin-spin correlators in the material, or the so-called dynamic structure factor of this material. And as a result, you can image locally what is the dynamical structure factor of these materials. The nice advantage over similar techniques like neutron scattering does this similar kind of things, but on a bulk level samples. Here you can use mesoscopic samples to do same thing using these NV centers. So that's one sort of advantage that this kind of sensor brings in. And here I'm just depicting the same protocol. What you'll do is you just shine green light on it, initialize it in this, let's say for the state 0, that's the non-equilibrium population of NV, and then you just watch it relax for certain time t and read out how much population is still remaining in the state 0. And as a result, that gives rise to curves, experimental curves. So this is an experimental curve example that looks something like this. As a function of time, this is just showing the population in state 0, which is changing as you're changing as you just let it thermalize. So you can initialize in state 0, you can initialize in state 1 or plus minus 1 by first initializing in state 0 and then using a coherent microwave to do, let's say, pi rotation, and then watch that particular thing relax. So you can get a level resolved how fast these things are relaxing, and that relaxation rate is governed by the spectral density of the noise. So you can extract by reading this relaxation rate the spectral density of the noise that has come out. Okay, so that particular protocol is called the relaxometry, again borrowed from NMR community. Okay, so that's what we will be utilizing here. So here's the experimental setup that they looked at, which was an insulating magnetic material. This is the yttrium iron garnet is an insulating magnetic material whose interactions are well known inside this material. So you can calculate the spectrum of these magnons, what is the dispersion of these magnons inside these systems. That's sort of well established. And then there's a strip line that excites these magnons inside the system. And what we are using is this NV center will be probed to probe the non-equilibrium chemical potential that will be used here. And here's the experimentally how this, yeah. Right. So this was, in this example, it was a single NV. So the system was, there was diamond nano beams that were deposited on top, and then you implant single NVs inside this diamond NV. Right. And there's this platinum for some spin injection experiment, which I will not be talking about, but this work also injected spin current via spin injection by platinum and detected that as well. Okay. So here's the essential physics that is happening in this experiment then. So if I now look at just the case without driving, just this film is in some temperature T, then I have a spectrum which is in a cartoon way represented by parabolic. It's a bit more complicated than that for IG, but all these magnons, the thermal magnons are just populated because they are at some finite temperature. This just represent the spin which is jiggling around in this material at some finite temperature. Right, and that's the usual situation where there's no chemical potential to talk about for them. This mu is 0. But now this strip line was designed to drive this band at its so-called FMR frequency, the lowest the coherent mode. And then if this drive will drive this particular mode over here, this particular mode is connected to all these sort of incoherent bands of magnons. if there is any nonlinear scattering mechanism that is there in these films, which usually happens because it's an anisotropic material. So as a result of that, this K mode over here, via nonlinear scattering, since I'm driving it, the energy and momentum will leak out of this particular mode and start changing the population of the finite gas of these magnons. It will be pumped. So it's like a pumping of these magnons that you're generating via driving, because these things are connected to each other. And that pump can be, in first order, can be just modeled as you have raised the chemical potential of these magnons if the magnons are still described by still the Bose statistics. So that is the claim, and then you want to measure this particular mu. Okay. Right. So now coming on to how do we measure this? So this omega plus and omega minus are the two levels that I mentioned. 0 to +1 is plus, and 0 to -1 is the minus transition of the NV center. Okay, so they are drawn here with respect to the band. So they are still inside the band. So whatever is the noise, spectral density of noise at this particular frequency created by magnons, that is proportional. That will be proportional to the relaxation rate. And you can again, just simple Fermi-Golden rule can calculate that relaxation rate over here. And as a result of this driving, if I am raising the chemical potential, the noise will change at that particular thing. And as a result, this relaxation rate will also change. Now, if you stare at the formula a little bit, if you just take the ratio of gammas in the presence of drive and in the absence of drive, in this case, the two ratios, all other prefactors in this case cancels out, and the effective chemical potential just directly spits out if you just take the ratio of with driving relaxation rate and without driving relaxation rate. This is all assuming nothing else is changing. So I'm not changing the spectrum of the magnons, and also assuming that I'm not changing the temperature. So drive can also change the temperature of these magnons. But that was sort of corroborated by a supplementary experiment that via the levels of power that were used, the temperature was not rising in these cases. So as a result, if one can utilize this formula to extract some quantity, let's call this chemical potential, that is what we could directly measure via this particular technique.
Yes.
Yes.
Microwave. So you are basically measuring T1
rho. Yeah, T1 rho. Right, that's right.
But instead, iterative equation, you have mu dependence also.
On this side? Yeah, so that mu dependence is again just known over here. So you can calculate it. So now, well, this is basically you just measure it, right? So in this, I'm driving it in the presence of drive. That's what term I'm calling gamma mu. Right. So this gamma mu is an experimentally measurable quantity, because I can just measure in the presence of drive what this is, and I can measure this in the absence of drive, and that ratio is mu. What is, sorry? F here, that's just the Bose distribution. N is sorry, right, you're right. So N is the Bose distribution in the classical limit. F over here is the filter function, which tells you which magnon wavelength will couple strongly. So to just give you some intuition about this F, if you have a wavelength which is very large, that is like the magnetic field produced by very fastly varying charges. So it's like a charge density wave. You can calculate the field, and that will just go to 0. Right? But on the other hand, if this F the wavelength is very, very small, again when wavelength is very small, then the charges just average out at the NV. But if the wavelength is very, very large, then it's like a capacitor, and you again don't see. So there's one finite wavelength that couples most strongly to the NV. So that's this filter function that describes that particular physics. Right.
What's this ratio?
This ratio? Right. So this, I'll just show you the exact numbers what mu comes out in this case. Right. So so that you can calculate again, because it's like a very straightforward calculation. That let's say we have spin waves, right? So that produces what I'm really interested in, what magnetic field it is producing at the NV. Right? So now if I have a spin wave, you have divergences of magnetization in the system. That divergence of magnetization in magnetostatic limit appears as magnetic charge, effective magnetic charges, producing an electric field at the NV. So you can just calculate for a oscillating pair plus minus charges, what is the magnetic field at by this technique. Again, these type of things were done way back by Klenikos and Slavin already. So it's just a simple application of that. FKD independent of what target material is? Right. Yes. it will be independent of what the target material. So this is just the, if I give you some modulated charge, what is the, right? Yeah. D is the density of states, right? So this will depend on this dispersion and whatnot. Right. So, so now you can experimentally measure this, and you can sort of model this also. And this is the theoretical model that was developed for that, where again it's a phenomenological model where we say that the magnon modes can be you can divide them into either a coherent mode, which is k equal to 0 mode over here, and that k equal to 0 mode is coupled with all these thermal magnons, a thermal bath of magnons. And the coupling between these two is parameterized by a model eta, parameter eta, which is like the non-linear interaction in this original Hamiltonian of the system. That will give rise to this coupling. But then this so now if I'm driving it, because of this coupling, I can pump these gas of magnons. But on the other hand, these magnons are also dying back to the lattice because of this just Gilbert damping in the system. So their parameter is like alpha, the Gilbert damping of these materials. So then it's like a balance of the two situations. So I'm pumping in magnons and they are decaying, and that in steady state will establish some finite value of the number of these magnons, which can be modeled as a chemical potential. And again, without going into much details of how exactly to do this, so this phenomenological model can spit out again a formula for, depending on this parameter eta, which is now a function of where my magnet points. So you can change that with the changing orientation of the magnet. So then you have some dependence of this mu expected based on the angle in which the magnet was pointing. And that is a parameter that that angle you can change experimentally also. So you can apply an external magnetic field and see how your mu is changing experimentally and compare it with the expected pumping formula that was derived here. Okay, so these two things is what, yeah. Sorry? No, not the NV spin. So magnet is broken down into this. So I'm right now just describing the magnet's dynamics over here. Right, so what I want to calculate is what is the steady state value of this mu produced because of driving it. So that's the system that we are driving. NV is still thought of as like a very perturbative probe. It is not really changing anything in the system. All right, so then we can compare these two things, experiment and theory, and here I'm just showing the exact experiments that were done. So this is the same protocol that we just discussed. You initialize in presence or absence of drive, you read out and extract the gamma rates. And here's are the values of gamma rates as a function of, so if you forget about this axis, first let's focus on as a function of drive power. And these are the typical numbers you can see for this gamma that you get as a function of drive power. And again, as I mentioned, you can change that by applying external magnetic field, because you can move the spectrum of magnons itself by changing the magnetic field, applying an external magnetic field. Also the NV center levels you can move by changing the magnetic field. Okay, so those are the handles that one can get. You can get these different rates, and by utilizing this formula that I just mentioned, from measuring in drive, in the presence of drive and absence of drive, you can convert these things into effective chemical potential that, let's say, we are extracting. And these are the curves that you get as a function of drive and external field. What are the chemical potentials that you get? Okay. So first thing, you can just compare it between the experiment and theory, the angle dependence, and with one fitting parameter of that eta. And what we saw was that it was giving the exact dependence that we expected. So that was just one proof, but sort of a more sort of self-consistent proof that this model itself is right or not is coming from the fact that if you look at the value of chemical potential you extract, so if you focus on this figure over here, as we are increasing the drive power, the mu starts rising. So this mu value is starting rising, but it gets go ahead and pinned at the bottom of the band. And that's what you typically would expect if this can still be described by a mu, because these are bosonic systems. I cannot go and punch through the band, right? So as a result, and so it got pinned, and we can do this experiment at different values of magnetic field, which is doing effectively changing the gap over here. Every single time it went ahead and got pinned at that value. So it sort of gave us an internally self-consistent proof that indeed this system can be modeled as some effective mu, and the number that we are extracting compares with theory well and always got pinned. So based on that, we sort of concluded that indeed this experiment is measuring locally a chemical potential. Now it's like a local probe, voltage probe for charges. Here it's like a local nanometer scale probe for insulating systems. And that is something which was not very easy to do before this experiment.
So if I may ask you about something more elementary.
Yeah.
In the previous slide, you showed the experimental setup, right? So there's an NV strip and then underneath there's a sample. So how do you apply this driving force or the driving?
Drive. So there is also this strip line over here.
Yes.
So this is just a microwave strip line, and you're applying microwave passing AC current through it.
Okay.
And that's how you're driving the magnon.
So what does that do? That makes magnons.
Okay, yeah. So that generates.
Move in a specific direction.
Correct. So that is that produces electromagnetic fields.
Okay.
But the strip line's dimensions are such that the wavelength of this are pretty large as compared to the micron size wavelengths of the magnons. So this can be almost thought for magnons as like an FMR type of drive for the magnet. Okay.
So before applying this drive, the magnons are, the spin waves are moving in all
Random directions, just
directions.
thermally populated.
Once you apply this, you're saying that there will be a net flow of magnonic.
Right. So you will generate a non-equilibrium population of these magnons, which will again in this geometry, which way it propagates, it will depend on the net magnetization direction. So you will see this way direction and that way direction, but it is non-reciprocal. So there is some non-reciprocity that you bring this one wavelength, this one direction is more efficient than the other one. So you do generate a directionality by driving this way. That was also demonstrated in the next experiment. But this is essentially can be just thought of as you're just generating some local chemical potential, and that is driving these magnons around.
So same microwave which is driving the NV is also providing the direction.
Yeah, so they this strip line could also directly convert the NV center to drive the NV center, and this same strip line is driving my magnons in this case. Yeah.
So if I were to take the analogy with the phonons, so you're not changing the temperature of the phonon bar, so the phonon population is fixed, but then somehow by hitting it periodically, you are generating more phonons. Is it something equivalent to that?
Yes, yes. You can think of it like this. Here the hitting is coming from the magnet itself. Okay, so I am driving, first of all, this AC magnetic field couples to the full magnet, which mode will you drive? That will depend on, okay, let me try to go back here. Okay, so this picture over here. Now this is this full band of magnons, right? So there is a k equal to 0 mode, which is like almost uniform mode of this magnet. Then various kind of finite wavelength magnons in the system. Now, if my drive is resonant with this k equal to 0 mode, I will drive that particular mode. So which I'm resonant with, only that mode is driven. So in this case, my whole magnet, you can think of it as driven like this. But this whole mode is also connected to all these finite wavelength magnon modes. If there is any non-linear interaction within the magnetic material, if I'm driving at omega, I can also drive at higher frequency magnons because there is non-linear interaction inside the system. So all the other magnons are driven by this AC oscillation of the magnet itself. So drive is not directly coupling. So this drive is not directly coupling to those magnons. It is via this. So it's like kind of like an evaporation process. So you are driving something at low frequency, and via non-linear interactions, these magnons are then driving higher frequency magnons.
Like those magnons are decaying scattering into plus k minus k.
Yeah, so they are. So that's exactly sort of the picture was trying to demonstrate here. So there's this k equal to 0 mode, and that there are all these various kind of magnons. There is some coupling between the two. Now, if I start driving, I will pump that energy through this coupling into the gas, and that sort of raises the chemical potential of this magnet. Right.
So IIG has been known to support these magnetostatic surface modes. So
Right.
So do you see any?
Yeah. So in this experiment, we are not driving at one of those modes. So it was still at the FMR frequency. If I change the frequency of this strip line, one could drive this propagating modes. And those was the question that I was like, can you change the directed modes? You can drive them also directly, like this. Yeah. So again, this is just a way to demonstrate that k equal to 0 mode can create a non-equilibrium chemical potential for. So actually, the experiment was done in reverse. this is the story I'm presenting, but the first experiment that was done in this regard was actually people did not expect. If you drive here, you should not expect NV center population. It's not resonant with the NV center. So there was one paper that was produced by Chris Hamill's group where they showed that if you drive with off resonant, you still affect NV center. And what is the reason for that? That was like an open question, which was trying to address here. But then they utilized that you can use this for also measuring chemical potential. Yeah. Mm-hmm. It does, right. So the frequency, these omega plus, omega minus, they will also move with magnetic field. Gap also change, and this omega plus, omega minus moves. So they relatively move with respect to each other. At some point, they will become off resonant, and then at that particular point, you will stop seeing much interaction between the two. So these are still, maybe I can show you the value itself, but on the order of still milliteslas. And so those are the scales, right? And now if you apply teslas of field, then they start to become off resonant. But that's also in a nice way because, for example, if you have, let's say, anti-ferromagnets or something which has very large gap, you can bring them in resonance if you apply a very large field. So systems which have very large gap could be still useful to measure this way. Right. All right, cool, thanks. So let me go to the second part, and most likely this is the in the second part of the talk. So the first thing I hope what I try to convince you is that you can use this to measure non-electron population of magnons, which currently there's only one way that is other known as this platinum contacts to measure this, but those are not really local probes. So here you can use them locally. Now the second topic that I want to talk about is there's also this field of anti-ferromagnetic spintronics, where you replace magnetic materials with anti-ferromagnetic materials. The whole advantage there is the anti-ferromagnetic dynamics is much faster because it's governed by exchange interactions, which are much higher scale as compared to for the ferromagnetic materials. So the frequencies of these excitations inside anti-ferromagnets is on the order of hundreds of gigahertz or terahertz range. Right? At the same time, the anti-ferromagnetic does not produce much stray fields, because it consists of two sublattices which are already antiparallel with respect to each other. So as a result, if you want to build, let's say, some sort of technology out of these antiferromagnets, you can bring them really, really close to each other without disturbing each other, because they don't produce these sort of stray fields. So as a result, people are very much interested in utilizing these antiferromagnets for various kind of applications. And again, a good review article here talks about this whole field. But the fact that there's not much stray fields coming out of this, the dynamics is such high frequency, the traditional probes of magnetism itself is very hard to adopt. For example, let's say if I give you an antiferromagnetic texture and you want to image that texture, it's very challenging for traditional probes of magnetism to do that. And what the main claim that we want to do is in this sort of theory work, what we proposed was you can still utilize these NV center noise relaxometry experiments to image antiferromagnetic domains. Right? And that we demonstrated with a simple model of, let's say if you have a domain wall of these antiferromagnets. So that's saying that on the left hand side, my antiferromagnet is aligned like that, and that changes to the opposite and changes in a smooth way, and you want to image such domain walls. Traditional like MFM or those kind of probes are not suited for these type of applications because stray fields are very tiny, if any. So how do I image these things? And the proposal what we had was, again, to do something very similar, to use NV centers, but now again look at the relaxation rate. So look at the noise coming out of these textures. It turns out the ground state imprints, the noise spectrum of these things can be affected by what the ground state that you're trying to measure, and that noise can still have the information about these ground states. And to illustrate that, and by the way, before I go there, I just want to show these are experimentally available systems where you can put these NV centers inside diamond pillar. And in fact, for ferromagnets, this was what was used to image like hard disk drives in ferromagnetic systems on the scale of about like 30 nanometers. And this is a real experimental system where on AFM tip you can implant these NV centers. These are also now commercially available that can be put in your AFM systems to do these kind of experiments. Right? But the idea here is, again, as I mentioned, the ground state changes the excitation of these systems. So very simply, we can understand this as the following. So if I'm on top of this domain, one of these domain structure, the domains are the typical antiferromagnets, which have very high frequency, as I mentioned, because it's governed by exchange interactions. So the gap of excitations in this case is much larger, is on the order of hundreds of gigahertz. At that, all those modes will not couple to my NV center because NV center is like gigahertz. So they are far off resonant. So they cannot couple to my NV center and cause relaxation. On the other hand, if I come inside the domain walls, the domain walls carry very low lying frequency. They are very soft modes of these antiferromagnets. In the very extreme limit, let's say no pinning in this material, I can place this domain wall anywhere inside these materials, and the energy does not change. So this is like the zero mode of the problem. And so then there is the Goldstone modes, both regarding the position of the domain wall, and these also carry spin, and spins can rotate. So these are easy axis antiferromagnets that we were interested in. They have this U1 symmetry of spin. So as a result, they also carry very gapless type of modes in spin. But that's in the situation when there's no pinning. Of course, in real materials, there's always some pinning, but the gap is then governed by the small pinning as opposed to the very large interlayer exchange, very large exchange interaction. So the gap could be very, very tiny as compared to that particular thing. So now as a result, if I scan and look at the noise that is coming out of this system, at the domain wall, you will feel more noise because there are all these modes that are available to you. But in the domain region, you don't see any of this noise. So if you just do a T1 map of the system, look at the relaxation rate, all the domain walls should light up, basically, where the T1 should tank near the domain walls, but it should not be there. So that was the main proposal, and we did some calculations for different materials. But recently, again, there was an experimental demonstration of this phenomena by Vincent Jacques' group in France. What they looked at is this is a very well-known stack layer for the spintronics community, which is so-called synthetic antiferromagnet they can create, where they have two domain walls which are anti-aligned via an RKKY or interaction governed in this material stack, and that generates an experiment. You can generate a synthetic antiferromagnet that way. And what they did was, again, with an AFM tip in this synthetic antiferromagnet, they did construct the T1 map, and whenever there was a domain wall, the T1 tanked, but whenever there was not there, so they were able to image the domain structure inside this antiferromagnet using these NV centers as probe. Okay. So I hope with these two examples, what I've tried to convince you is that these NV centers could be used as sort of new probes for condensed matter in general, but spintronics in particular. And maybe in last 5 minutes that I have, I'll just go towards this very quickly talk about this other experiment, where our goal was to sort of, so far what I have talked about was still imaging magnetic materials, magnetic signals out of these things, but can we extend these nice capabilities to other kind of materials? And there our central idea is to do something that we call hybrid sensing, where the idea is you still use a magnetic film, but now this magnetic film acts like another probe, which can couple to various other degrees of freedom via spin orbit interactions, for example. So for example, charges coupled to this magnetic field, magnetic spins via spin orbit interaction, and in systems where such interactions are strong, you can use this to even detect charges, because the idea is now charge will talk to your magnet, and magnet will talk to your NV center, and as a result you can image or measure different kind of other materials. And here, as an example, we took a ferroelectric. If you want to, let's say, measure ferroelectric with NV center, the charges can directly also couple, by the way. There is a Stark shift that happens, but that strength is very, very tiny in these typical materials. So what we do is, on top of ferroelectric, we put again a magnon bus. In this case, it's a cobalt iron boron material, which is again a very well-known stack in the spintronics community, where now the central idea is, if my voltage couples to this electric polarization, I want to image what this ground state of this electric polarization is. If this electric polarization changes, it changes the magnon spectrum. And the way it changes magnon spectrum is via spin orbit interaction. Physically what happens, this is a piezoelectric material. So if you apply voltage, you can change the value of polarization. To accommodate the change in polarization, the material expands in one direction and shrinks in another direction. And as a result, you build in a magnetic anisotropy on the magnetic film. And this magnetic anisotropy changes the gap, or you change the spectrum parameters. In this case, you just simply move the gap of the magnons, because the gap depends on the intrinsic anisotropy, magnetic anisotropy of the system. So as a result, what is effectively happening is the polarization is affecting the magnon gap, which is affecting the noise at the NV, and then this polarization gets detected via this sort of hybrid scheme. So that's the essential cartoon way of showing what we are doing in this experiment. And let me just directly come to the experimental result here, which is this one, where depending on the state of the polarization, whether it is pointing up or pointing down, the gap of these magnons was affecting in this system because you imprint an anisotropy, as I just mentioned. And in one case, the NV center were off resonant. In another case, they become resonant. So the T1 time changed as a function of voltage in the system. So this can also be viewed as you can tune the coupling between magnons and NV center by an electric field in this case. In all previous structures, it was fixed by what distance I am away from this thing. But now one can tune it electrically in these cases. Right? And that could be viewed also as a sensor of electric field or electric voltage, a hybrid sensor of electric voltage and electric field. And when, yeah. So.
Is this like more sensitive than say piezo force microscopy?
So we did not compare it with piezo force microscopy. Again, here the advantage is you could also do dynamic excitations. You can probe dynamic excitations, and those kind of things are the more advantages. We did not compare with that, but what we wanted to compare it with was what is the bare direct NV electric field NVs can sense, and via this hybrid sense. If we compare the two, what we saw was here if we can get up to, by properly designing it, we can get about an order of magnitude improvement in electric field sensing capabilities of NV centers. So that was the main result of this particular work. Now, since I'm out of time, I'll just probably flash the final slides. So those three works,
you have 10 minutes.
Oh, I do have 10 minutes. Okay, cool. Okay.
Do you have any picture of the device, actual device, where the NV is shown?
Oh yeah, unfortunately in this one is really all cartoon pictures. The only device picture I put in my slide was this one, but yeah. Again, I'm happy to share and talk to you about what. So the device was actually nanodiamonds. In this case, it was not single NV used here. This was an ensemble of NV centers, and these nanodiamonds were drop casted on top of these films. In this case, okay. All right. So the final work, maybe I should, in the remaining 10 minutes, I want to talk about this, the non-reciprocity aspects of these things. So far I've talked about NVs as just probe of these various kind of excitations in different materials. But what people are also now getting interested in, let me go in the quantum level of magnets. Let me cool down the magnetic system in the millikelvin range. So gigahertz frequency tells you should be in millikelvin range to go to single magnon type of limits. And in that case, two NV centers can be coupled via magnon bus. And you can create entanglement between two NV centers via magnons. The advantage of that is if you want to directly entangle two NV centers, you have to place them really close to each other. The direct dipole coupling falls off much quickly as opposed to the coupling mediated by these magnon modes of these films. So same ideas people have tried with phonons, coupling NV center with phonons, but here the phonons don't carry, the phonon coupling with NV is also very tiny, but magnons directly couple with the Zeeman coupling, and which is much stronger. So then the idea is potentially you can create two entangled states of NV centers on chip with these magnons. Right. What we wanted to highlight here was more than that, this is also non-reciprocal coupling. The reason for that is a magnon which is moving towards the right and a magnon which is moving towards the left couples very differently with the NV center. And that essential physics was again very much well known in this so-called Damon-Eschbach mode that Sunil was also mentioning, that if I have a magnon mode in thin films, and again these are just classical magnon modes, in thin films moving in the -k and +k direction, you can, it's like a wave like that, right? And from this magnetization profile, you can calculate the field that they will generate, which is the divergence of M if you take over here, apply that to magnetostatics type of approximation. Divergence of M acts like just magnetic charges for your calculating this field over here. So wherever there are divergence in this magnetic profile because of this excitation, that produces some effective magnetic field. Okay. So that produces some effective magnetic field at the NV. Now, if you generate a wave, properly look at wherever the divergence are, well, there's divergence in the bulk coming from just this term over here, but there's also divergence at the surface of the magnetization. So then at the surface also you create these effective magnetic charges, and on the bulk you also create these effective magnetic charges. Depending on whether you're going in -k and +k direction, the charges in one case add onto each other, and in other case the charges subtract from each other because there's k dependence of this charges that is there. And so as a result, the effective magnetic field that you generate at the NV location will be of different strength if it is moving in the positive direction or it is moving in the negative direction. Okay. On top of that, the polarization of this field. So this is like a sliding charge density wave. which creates an oscillating field, the polarization will also depend on the direction of this magnetic field. Okay, so that's the main takeaway. That's very well known from the magnetic community, that the field strength and polarization depends on the direction in which the magnons are moving, right? And on top of that, in NV centers, if I look at the two levels that this NV center holds, 0 to +1 and 0 to -1, they are also sensitive to the polarization of the field that they are trying to sense, because of this intrinsic zero field splitting that is present. Right, so if I view this intrinsic zero field also like a Zeeman-like term, it's an effective additional built-in magnetic field, which if you just take the derivative here, it's spin dependent, SZ dependent magnetic field that exists in the system, and whether spin is +1 or -1, the field points up or down in this NV center. So as a result of that, there is a built-in handedness in the NV center. One of these levels couples more strongly to one circular polarization, the other level couples more strongly to other circular polarization. So then if I bring these two facts together, the fact that if I have an NV on top of a magnon, if it is moving towards the left, it will couple more to this transition. If it is moving to the right, it will couple more to the other transition, just by combining the last two previous facts that I mentioned. So then can we show this sort of non-reciprocal coupling, direction-dependent coupling between magnons, was what was the main motivation here. So again, this was what we proposed to, again, use relaxometry as a measurement, because now the relaxation rate here is between, if you resolve the relaxation rate from 0 to -1 and 0 to +1, which can be done experimentally, because you can initialize either in 0, +1 or -1 and extract each of these three levels out. You want to show that the two rates are very different, even when their energies could be same. So if the magnetic field which separates these two +-1 is very, very tiny, it approaches 0, the relaxation rate should be same if it was not reciprocal, but you should see a non-zero, non-equal relaxation rate. And this was the experiment again that was performed on nickel thin films by our collaborators in this case. And what they did observe was, as the field was approaching 0, the two rates starts diverging with respect to each other, and there was indeed some sort of non-reciprocal coupling. As a side advantage, what we got out of this was, if we include this sort of non-reciprocal coupling, which was missing from previous models of coupling NV center and with, we could fit all the possible experiments that were performed experimentally without any adjusting parameters. So earlier people used to adjust their parameters, an overall parameter, to get fit to the experiments. But if we built in this physics, we produced very nicely all the literature relaxation rate that people are measuring in this system. So with that being my last message, let me just come directly to the conclusion then. So I hope with these examples, what I've tried to convince you is, first of all, NV centers are very nice new type of probes for sensing magnetic materials specifically, but in general, you can use them for basically any magnetic noise. You can think of it as like you're performing a neutron scattering experiment in different frequency range and different wavelength range. So you can get structural dynamical factors in different wavelength and omega for various kind of target materials which generate a magnetic noise. Okay, so this technique, people are now very excited to apply it. The questions that people are looking at is, can we use this to, for example, probe more exotic states of magnet like quantum spin liquids, because there the noise, the temperature dependence of noise will be different depending on whether you have bosonic excitations versus spin-on-like excitations. Can you use that to extract the temperature dependence? Can it be used to extract some information about what are the excitations, whether they are fermionic or whether they are bosonic? At the same time, 2D magnets is another field where these NV centers are becoming very, very interesting, because 2D magnets have very low absorption cross section, because they are very, very tiny, and there comes in some flakes, which is also very tiny. So again, all traditional probes of magnetism which want to measure dynamic properties of these systems, like neutron scattering, for example, if you want to extract structure factors, are just very challenging to adopt to this really monolayer, bilayer system. You need crystals for that experiment, bulk crystals. But here you can use NV centers to do similar type of experiments and extract information about it. Again, here just a picture shown of, it's still a work in progress. We have not finished this, but we applied this on a 2D magnet over here. And in fact, the defect centers here we were using was not NV center. These are the new kind of HBN defect centers that people have also seen optically active centers inside HBN. The advantage HBN further brings is you can create, they are already there to protect the magnet, and they can be brought very, very close to the system, because the resolution depends on how close you can bring them. So then you can potentially get better resolution. And what we believe we are seeing in this work are are sort of these domain wall magnons living inside these FGT films. Again, I should not make that claim yet before we sort of make that more clear. But the whole goal is the field is trying to use these NV centers for probing various kind of different quantum and topological materials. There are interesting ideas of using maybe like edge states, magnon Hall effects, and things like that. You can measure topological magnon states, things like that, using NV centers as a probe. And that's very exciting to sort of see what is happening. And on the flip side, these now novel excitations could be used to even sort of maybe entangle NV centers and create states which were not previously possible. So this is a very kind of nice outlook and a lot of things to be done here. And I hope I've tried to at least give you a glimpse of it and show that this is really interesting. Yeah, thanks. Yes.
So in HP, first of all, thanks for your talk. I was present just in the last 10 minutes.
Right.
So in HPN, what kind of vacancies are these?
So these are boron, thought of to be boron vacancies. Again, these are very new centers, so people are still trying to figure out. So, but the one that we believe it's boron vacancy center. But we believe by the mean that from DFT calculation, people have shown if you have a boron vacancy center, its level structure, its spin structure seems to match with what people have measured. So it's a vacancy of boron, and similar to NV, it's BV minus.
Okay, so they also show up in luminescence, and there is a zero phonon lines and side phonons and so on.
Yeah. So it looks very similar to NV center.
I see. And in which wavelength range are these?
So again, very similar. So again, green to.
So even the wavelength range is similar.
Yeah, it's a somewhat different, meaning in the sense it's much. I think so. NV center is green 532 is the one, something like that, right? So and this one is about like 500 to 800 that range. So it's still invisible. So it's fluorescence. It's same type of experiments that people do. The only difference that people have measured, if it is a spin, so there are many zoo of defect centers inside HBN. So you have to properly create a spin defect, and that spin defect turns out to be very dim. So the rate of relaxations, the dark path versus this path, is very different. So as a result, they are very, very dim, and that's one challenge that people are facing. But another experiment that people have done is you use plasmonics to enhance that rate. So you can further enhance, still not reach NV center levels, but it's still reasonable. You can do experiments and see.
Oh, interesting. And in these experiments, what are the temperatures which you need to?
So again, as in the initial part, I mentioned that these work from all the way from zero, so cryogenics to room temperature. HBN, again, so this experiment that we did was actually a temperature dependence curve. So we did up to, in this case, we did, I think, go up to like 70 Kelvin, but you can further go down.
So you can see the luminescence at these elevated temperatures.
Yeah, right.
Okay.
Yes.
Oh yeah. So why is there no selection rules for the left moving and right moving? Why does only 0 to +1 and 0 to -1 get excited? The two.
So if you have perfect circular polarized radiation, then because of the zero field splitting that. Sorry?
These transitions are due to coupling to the magnons.
Due to coupling to magnons, yeah.
So the
Magnons produce they will produce an slight elliptical polarization. So what I presented was an ideal picture. There is always some crosstalk between, so there is a gamma plus both cause, but one of them is much more efficient than the other one because they produce elliptical polarization.
field generated by the magnons,
That has a polarization, yeah. And again, this can be thought of as just simply because of these magnetic charges. These are like a charge density wave, and this charge density is sliding. So from plus to minus, let's say you have a field like this, and if I just keep sliding it at one center, I'm just rotating the field. So that's the type of fields you generate. Yes.
So even without external noise, NV center already has its internal relaxation.
Yes.
So if you take ratio even without noise, ratio of with drive and without drive, you still get something.
Right.
Now how do you separate drive with external?
Right. So the intrinsic noise turns out. So for all these experiments to work, the intrinsic noise is your flow, right? So you need to can you change that dramatically? In this case, it happens that the amount of change you get from the basic level is much large. Is very good quality. Yeah. So the contrast is very large. No, okay, so two things. So one thing is these diamonds, like the intrinsic was about 200 microseconds or so, or on the order of milliseconds, the relaxation rate. And the one in the presence of magnet came down to about tens of microseconds. The coupling is pretty strong with this. So the fact that coupling is very strong and intrinsic was about hundreds of microseconds, that difference gave the rise to the contrast, and we were able to see it. But if the noise itself is very weak, then you're absolutely right.
You mentioned entangling two diamonds with magnons. What was the distance between?
Oh yeah, so by the way, I should mention that's just a theoretical proposal, not seen experimentally yet. So the experiment showed about, the theory proposal shows about micron scale you can still get. Maybe I can show you one picture and that would sort of better explain that. So this is, by the way, not my work, but this work is from Oshlum's group. They did a theory calculation here in combination with Flate's group. They did a theory calculation. This is one of the works. Earlier, Daniel Loss has another work which does exactly the same type of calculation, but they were more like model systems. Here, they actually look at what IG is there. And then the main curve that I'm trying to show is this effective coupling as a function of NV distance. If you look, there's this gray line over here. That is just the direct dipole-dipole coupling. And if you calculate for the design structure that they were looking at here, what is the coupling in presence of for magnons, that's the coupling that they got. So you can expect up to some sort of micron distances you will be able to do it. But of course, one has to compare this with what cooperativities you'll get and all that. That is still experimentally demonstrating this is a challenge right now, and people are looking into these kind of things. Yeah.
So why is this oscillatory as a function of time?
Yeah, that's a good question. I haven't looked at that part. Yeah, sorry for that. Yeah. They might be particular design related. There might be some interferences going on for that particular day.
Is that the wavelength of magnons?
No.
Wavelength of magnons is on the order of like tens of micron meter, typically, in this IG film. Yeah, but this is still, I would say, like a micron or so. Much less. Typically, it's like tens, like 20, 30, that kind of. Yeah, I have to look into the exact details, but the main message I wanted to give was that you can extend it.
So, in the slide you were showing about anti-ferromagnetic domain work. So, you showed a artificially made structure. Do you have reports on a natural anti-ferromagnetic?
Yeah, so
I wouldn't expect a domain wall which is on par with a ferromagnet. Like, there is no reason for an anti-ferromagnet to have that kind of domain wall. So, electrostatic reason.
Right. So meaning, are you saying that in anti-ferromagnets the domain wall will not have the same structure? Is that what you say?
Should not be like. So you showed on artificially made structures which are similar to giant magnetic resistance. There, it's okay. RKKY. So I was just wondering whether you have such domain walls in.
Yeah. So these type of domain walls will occur in easy axis magnets, easy axis anti-ferromagnets. So like MnF2 most likely. But the principle is generally valid in the sense that domain wall could have a more complicated looking structure. Those are much softer modes as compared to this. So for a specific system, we have to go ahead and calculate it. So chromium oxide, which we were wondering to show probably there.
Then you would have magnetoelectric domain, which
Right.
is fundamentally different from this domain.
Right,
You
right.
have 4 spin which are 2 up, 2 down, or 2 outside, 2 inside. So that would be very interesting to do with this.
Right. So chromium oxide, we also were thinking about.
Get some result on
Not really. So we haven't like actually went ahead and did this experiment yet, but we need to understand, as you mentioned, the correct domain wall structure there in the system. So that is something.
fundamentally different from what we have for a ferromagnet domain wall.
Right.
It's really different.
Right. And then there's nickel oxide is another interesting material that we think. So all these, and specifically also maybe, so there's one recent experiment on Fe2O3, and they are able to measure like spin transport, but not domain wall. In their case, they are measuring just, it's a applied magnet in the canted antiferromagnetic phase. They are measuring the.
Easy there, because canted antiferromagnet, again you have good reason to form, which could be measurable from NV center.
Right.
That perhaps I will look into that.
Yeah.
Thanks.
More questions? Last and final call. Okay. So if there are no more questions, then let us thank Pramey. And since Mukul has left, So I have the enormous responsibility of handing you over a small memento.
My name is Vijay. Unfortunately, I have to leave tonight around 12. I'll see what I'm going to department. I'm here. I have a class.